I don't know about you guys, but I feel like it's been unusually hot and humid in Maui this week. I guess that's compliments of El Nino, but we have 5 hot presentations for you today, so I hope you will enjoy them. Our first talk is by Vladimir Sotnikov, who's from AFRL in Dayton, and he's going to talk to us today about subauroral ion drifts.
Good day, I am from Air Force Research Laboratory, Sensors Directorate, and I'll talk about generation of short-scale disturbances in the ionosphere, especially in mid-latitudes, and how these disturbances can affect propagation of high-frequency waves. And this is what about in sensors here, because we're about interaction of high-frequency wave with media and radar, and also millimeter waves interaction, GPS. So this is the title of the talk, and yes, we have also, these are our collaborators from companies. Yeah, so outline of the talk, as I told you already, is generation mechanism of plasma density irregularities in mid-latitude ionosphere, and propagation and scattering of high-frequency wave and plasma with density structures. And what is new, what we are trying to do here, because usually when people study ionosphere, they took into account global models and large scales. But for us, it is important to take into account generation of short scales with wavelengths comparable with the wavelengths of high-frequency waves. And how we did this and what are the results, I will show you during the talk. So mainly we will discuss space weather events and subauroral ion drift and subauroral polarization streams, and how they can affect generation of low-frequency disturbances with short scales. Then we will study also generation of low hybrid waves with flows with velocity shear. Low hybrid waves, they are waves from VLF diapason. And also we will discuss scattering and propagation of high-frequency waves through this media. But media is, very specific, because during nonlinear development of excited waves appear different types of nonlinear structures. So in fact, waves will interact not with small-scale irregularities chaotically distributed, but with some structures which have long-scale correlation lengths and also accompanied with short-scale turbulence. So this is the difference, and in fact, these models of propagation are not built yet, and we are moving in this direction. So, and goals are linear and nonlinear stages of Kelvin-Helmholtz instability, excitation of low hybrid waves by flows with velocity shear, interaction of high-frequency electromagnetic waves with these structures, and also for validation we used fully kinetic particle and cell simulations to analyze scattering on developed density structures. And finally, ray tracing analysis when waves propagate through a media filled with vortex structures. So there are 2 paths in we are interested mainly in mid-latitudes. In mid-latitudes, there are 2 paths. One is high latitude range closer to the auroral region, and the low latitude range, it's related to equatorial spread of events. So here, what mainly we will be interested in, here it is a reconnection region, and from here, for example, injection of high energetic particles takes place, and they interact in plasma pulse. They interact with cold plasma inside the plasma sphere, and they can generate different types of disturbances and also from low hybrid range. And then these disturbances along magnetic field lines can be mapped to F region in the ionosphere. Here will appear electric fields which can create V cross B drifts, which are responsible for generation of different types of low frequency waves. And also they can create density gradients, which are responsible for interchange type instabilities. And this is the example, one of the examples how these effects were detected at first here in the plasma pulse region, and these are satellites from cluster mission. And like 10 minutes later, it was detection of the irregularities which were excited in this region. They came here and here. And here we see this is low hybrid drift instability, which appears when hot plasma is penetrating through the plasma pulse, and it appears here fields, and they are mapped then to the fields here in F region. And so in F region, in this way, can appear low frequency irregularities. And similar measurements were made by Sinov satellite in equatorial region, and this measurement is here, it's stretched. And you see appearance of short-scale irregularities with wavelengths which can be comparable with the wavelengths of high-frequency signals. And our aim is, first of all, to discuss what are generation mechanisms of these irregularities, and then how they can affect propagation and scattering of waves. So these are the basic equations which we used, and it's to fluid MHD. But what is important here, to include short scales, we need to include magnetic viscosity tensor here. It's like Braginsky terms, which can take into account one thing, even finite beta plasma. So these equations can be applied not only for ionosphere, but in high energy density physics. And also they take into account final Larmor radius effects, because ion Larmor in the ionosphere, it's about several meters, and this is comparable with, say, radar wavelengths. And that's why it's important, if you want to describe short scales, to include these terms, what makes, of course, equations more complicated. But we did this, and finally, these are nonlinear equations which describe excitation of Kelvin-Gergolitz modes and simultaneously excitation of interchange modes. And next. Yeah, first we can speak about excitation of Kelvin-Gergolitz tight instability. So we have, we have flow with velocity shear, and this flow appears due to E cross B drift, and E are fields which appear in the ionosphere due to this mapping which I discussed before. And then we can have, just for Kelvin-Gergolitz, more simplified equations which can be derived from the equations I had shown before. And we use numerical scheme. What is important here is that there are complicated nonlinear terms, and we use the Arakawa method to treat Poisson bracket nonlinear terms. It's vector nonlinearities. And eventually, these are some simulation results, how with time appears density regularities and contours of vorticity. So vortex structures will appear, in fact, and this you can see. And next, here you can see how instability develops. It's a linear stage of instability, then it's going to a nonlinear stage, and on this nonlinear stage appears vortex structures. So these vortex structures are specific in the sense that they can be extended, but motion inside the structures is coherent. So It means that when you build propagation model for high frequency waves to propagate, it's necessary to take this into account, because now what they use, it's usually phase screens which are only two-dimensional and have no third dimension, what is in fact incorrect. And here also nonlinear development of the structures and the appearance of wave spectra in density. Why we're interested in this wave spectra? Because they are used in calculation of scattering cross-section when high-frequency waves scatter on these irregularities. Next here you can see also this wave spectra and the dynamics in time, and you see that you have very strong flow of energy to shorter scales or large k with time. So from 10 to 6 you can go 10 to 3, so many orders of magnitude. And next, a few words about interchange instability, and this can be related to the subaurora region as well as to equatorial spread F. And the nature of this instability, in fact, it's instability of fluid with larger density above the fluid with smaller density, and this is happening also in the ionosphere. Here is the gradient of density is going this way out of the Earth. This is the gravitational force. Magnetic field is perpendicular to this plane, and this leads to appearance of instability. It's called interchange or Rayleigh-Taylor type. And what is, this is very specific instability which allows you to have spectra transfer not only to short scales or large k values like here, but also to large scales. And it's not Kolmogorov spectra, so it's necessary to build new theory for turbulent spectra for these types of instability. They use so-called predator-prey models when your interaction of part of the spectrum here can immediately transfer you to this region, for example. And here, what is happening if you start simulation with noise, but with given density gradients, which were taken, in fact, from experimental data. And you see how with time develops instability and appears nonlinear structures. So these structures are elongated along magnetic field, but in perpendicular direction they have finite size, and this is what is in perpendicular direction. And all this is along magnetic field. So in fact, waves interact with these types of structures. It's necessary to build model how they're interacting. So these are also the spectra which develop during this type of instability. And there are some also nonlinear solutions which can be obtained for these nonlinear structures, but of course there are many other solutions. It's one of the examples of solutions, but better for us to deal with numerical solutions because they represent reality better. And another type of instability is instability with much higher frequency. It's low hybrid or from very low frequency range. And they can be excited by flows with velocity shear. And this topic we had joint grant with NRL from FSR, and now we're continuing on our own. And here I'll show you example. If we have flow with velocity shear, before it was flow of electrons and ions together. Now here it's flow of magnetized electrons through ions which are not moving, and that's how more higher frequencies are excited. And you see nonlinear development of this instability appears much higher amplitudes, and if we did also 3D for this, and this is how it looks. So in fact, waves in 3D propagate through these types of coherent soliton type structures. like you see here, but they, of course, their size is much smaller because these are low hybrid waves, and this is related to GPS signals if you want to, or some other signals with centimeter wavelengths. So now a few words about refraction and scattering, because the refraction and scattering in plasma is different from scattering in the atmosphere, like people do RF scattering in the atmosphere or laser scattering. But difference is that in plasma can appear currents, and these currents can excite by themselves waves. And this is the reason why, except of in atmosphere you have refraction scale and you have diffraction effects. But here it's also one more channel. It's related to scattering in plasma of waves. It's called sometimes transition scattering. So for this, if we have incident wave, and with this parameter, this is the field of the incident wave, and then we can calculate what is the power scattered by fluid vortex, because we have these vortex structures, and this is the way how to calculate the scattered power, because you have a nonlinear current, and work of this current on particles will create your scattered waves. And scattering cross-section is defined like ratio of scattered power to this flow of energy of the incident wave. And what is different from atmosphere, say, because in atmosphere you have only this condition you should have for scattering, but in plasma this is additional condition on frequencies, and in fact appears frequencies which are different from the frequency of incident wave. And when this frequency shift due to, this is the low frequency turbulence frequency, when it is comparable with the frequency due to Doppler effects, which you have, for example, when radar is working, then this interaction looks like clutter. It's one of the examples. And here also, when in plasma, because this frequency of scattered waves usually is small, then in this case it's mainly scattering in angle, but not in amplitude of the scattered waves. And in this way, then eventually, if you know the spectra of low frequency turbulence, you can calculate scattering cross-section. And here it's presented. So what we did next, we tried to calculate scattering using peak code, and this is and compare results with theory. And we did this, and you see a pretty good comparison between scattering cross sections. And finally, also we learned how to make scattering from when we have not analytical but numerical solution for low frequency waves. And time is running out. And last example, it is refraction of high frequency wave on vortex structures. This is when we have small density variations, and this one is large density variations in vortex. And this is how it looks in 3D when it propagates the wave through the media here filled with vortex structures. And now this is the conclusion of my talk, but I already told about this. First of all, we investigate a mechanism of generation of low frequency waves, and second, how this can affect propagation and scattering of high frequency waves. Yeah, thank you, and if you have questions, yeah, I'm ready to answer.
Good morning. I am Kevin Jim. I'm giving this talk for Edward Peer, who's the PI in this project. The project is funded by NAVAIR, Patuxent River, by Robert Borland. And we are in a phase 2 of an SBIR process, hoping to go on to a phase 3 next year. And here you can see what our camera looks like. Oops, I hit the wrong button. So the camera consists of gold-coated optics. These are aluminum mirrors that can see the entire sky except for an obscuration caused by the position of the secondary mirror. And that defines a cone that has an 11-degree half angle across the zenith. However, we have ways to get around that problem so that we can actually see the entire sky anyway. This is based on the work of Peter Lewis. When he was a graduate student at SLAC, he built a system called Racicam that was located at Cerro Tololo and was used for a couple of years to do all-sky imaging. Well, we've taken his design and evolved it. So MAMBA is a tortured acronym. It stands for Meteorological Atmospheric Measurement Bolometer Array, but I just call it MAMBA. And once again, it gets thermal, infrared, all-sky images. We're using a commercial off-the-shelf camera from FLIR. It's a 640 by 480 pixel device with about a 25 millikelvin NETD. The primary purpose of this system is to measure the transmission through the atmosphere at thermal infrared wavelengths to any arbitrary line of sight, to any arbitrary altitude. Hence the design where it's an all-sky camera. Of course, it will do other things in the process, and we'll talk about that as well. We're hoping to commercialize this in the sense that we will make it available. Obviously, it's not going to be an iPhone, but we hope to sell a few of them. So as an astronomer, my first thought about an infrared camera was, well, let's use it to look at the clouds. And that was the original purpose of the first two cameras that were built previously. And you can plainly see the clouds here. They have a very different temperature than the rest of the sky. They show up very well. And you can use that then, slave it to your observatory control system to shoot holes, something that is very painful to do manually, but hopefully we can do this automatically all the time in the future. And there are observatories that do this. Notably, I believe GEODS does this. But this is very important as telescope time becomes more and more expensive. As I mentioned before, only a few have been built. Here we see the predecessors of MAMBA, the Magnum cloud camera, which was built by the Japanese and installed on Haleakala, and Racicam with Peter Lewis, our collaborator here at SLAC. You'll see that his mirror also is made of aluminum, looks very similar to the current MAMBA design. So MAMBA has evolved from Racicam. It's a higher resolution system, approximately twice the resolution angularly, and is much more sensitive. And we've also put on better coatings on the mirrors to increase the sensitivity of the system. And we've done a lot of work on tolerance analysis to reduce the distortion of the system as well. So one of the unique things about this design as compared to many other all-sky telescopes is that it's equiresolution. And that means that every single pixel on the sky subtends the same solid angle. So in order to do that, and there's been some research on this over the past 30 years, it's essentially a solution to a set of differential equations, which we then further optimize in a Zmax optical design package in order to reduce the distortion. But we successfully maintained the equiresolution such that with this particular camera, we're getting about a 0.4 degree pixel on the sky. And then we went ahead and created a lookup table from this, which we could input into a CNC machine. This is not a classical telescope, and it doesn't work the way most telescopes do. So it's a little bit difficult to make it work with the existing design software. But because we are operating the thermal infrared, we've severely relaxed the surface roughness requirements to the point where we did not have this built at an optical design house. Instead, we had it built at a good machine shop. And after we put a layer of gold on this, it's been further polished and all down to, I believe, approximately, we're expecting better than a 10th wave. So what does the IR transmission look like? As you go across the spectrum from here, this is 8 microns all the way out to almost 14 microns. You can see that the total transmission is dominated by several species. We have carbon dioxide, ozone, and water. Well, it turns out in our research, it appears that carbon dioxide, except for monotonically increasing until we're all underwater here, isn't really changing all that much on a daily basis, and neither does the ozone, but the water is highly variable. And so we concentrate on looking at the effects of water in IR transmittance. And sure enough, here it is. It's very variable. Here we have 0, precipitable water vapor column of 0 millimeters all the way up to 60. And you can see it's oscillating quite a bit. And that's no surprise. So the transmittance is highly variable, and it's due to the water vapor. In fact, we can see that if you do the propagated transmittance through any particular filter of interest, it varies from 0.4 to 0.9. Obviously, it can drop to 0 if you have thick enough clouds, but this is referring to clear sky conditions. So this poses a problem for remote sensing and instrument validation, and that's why NavAir talked to us about this problem. And their concern is calibrating their remote sensing imagery taken from aircraft. In this case, we're looking at the F-18, but it could be any aircraft or any other platform that's airborne. So what they would like to be able to do is know the accuracy of their imagery in a radiometric sense. And so this is one of the key capabilities to be able to do that. The current methods of being used to measure transmittance are all related to measuring water vapor, since water vapor is the dominant species that affects transmittance at these wavelengths. So radiosondes are balloons, as depicted in this picture here, that fly very cheap instrument packages. Those are flown twice a day at the same time from well over 10,000 different stations around the Earth. And there's an international agency that coordinates this, and all this data is available for downloading. And it's a great source of information. And each one of these packages, I think, costs about $100 or something like that. That's great, but it's flown twice a day. And it only goes in one direction, which is straight up. So that doesn't cover us for all the different sorts of lines of sight, and it's only twice a day. So we'd like something that's a little bit better than that. LiDAR would be very effective. We talked to some vendors, but it's extremely expensive. Likewise, FTIR is also very expensive, and the vendors who are building these systems told us it only works during the daytime. And GPS is very intriguing because it is all over the sky, but it is still limited lines of sight. And that methodology involves using, I think, effects of the phase delay or the time delay in the signals from GPS through different thicknesses of atmosphere. There's also satellite methods for extracting water vapor, which you could then translate to transmittance, and that's great. However, once again, the resolution is coarse because they're higher up, and it isn't quite as specific as what our customer is looking for. But these are all good sources of information, and the more of these that you combine, probably the more precise answer you can derive. So our methodology is based upon some radio transfer research we did. First off, assuming that the atmosphere is optically thin, at least in the upper atmosphere, above the ground layer. Absorbers are emitters, so we can model them very easily. The thermal emission from the sky indicates the precipitable water vapor content. And this is something that was established as far back, I think, as the early 70s. And there are papers, actually, where people are routinely measuring precipitable water vapor using simple, single-element thermometers, basically. But by using the thermal emission, we discovered that we can constrain the transmittance at those higher altitudes above the ground layer. So this drove us, as part of our solution, to building MAMBA, the telescope, along with a COTS camera from FLIR that allow us to measure this precipitable water vapor column. But that, of course, doesn't give you the actual final solution, and it gives you quite a range of solutions. So we have to further constrain it. And we do that, secondly, by using the ground level weather. So the ground level weather does a lot to affect your ability to see in the infrared. For instance, you might have very thin layers of fog, or you just may have a lot of humidity. And the humidity, remember, that water vapor is the key component that we have to look out for. So near the ground, that weather data is really important, and also the historic weather data on the ground over time, which influences the presence of aerosols and other things. So we need to add that in there. So we've added a weather station, which will record all that data. The third step, then, is to combine those two pieces of information along with radiosonde flights and put them into MODTRAN simulations. So MODTRAN is an accepted moderate resolution atmospheric modeling code used for radiative transfer. And it's been validated many, many, many times. And we've had extensive discussions with the authors of ModTran in order to get all our parameterization correct, because ModTran has, literally, if you set it up in all its possible modes, thousands of parameters that you could set. So it took a while to get it right. So once we did that, we looked at particular sites for the Navy, picked one, gathered weather data for it for 25 years, input that into ModTran, and ran many, many, many thousands, it might be millions of ModTran runs on a supercomputer in order to see what the results would be. And we then took all that, combined all these sources of data, and put them into a neural net and trained the neural net. And after a couple of days, the neural net spits out the answer, and then we have a solution where we can actually determine the transmittance to any altitude using only measurements on the ground plus radio flights, which are occurring anywhere. So here's an example of the results. On the left here, the black curves indicate a bunch of different possible profiles. This is the transmittance at 10 microns, I think we're looking at here. And this is the altitude in kilometers, up to 10 kilometers. So we're looking from 100% transmission down to 0. And so this is transmittance between the ground to that particular altitude. What you see here in the black are a bunch of different possible things that could occur at that particular site over the course of that whole historical period of time where we're modeling it. And those are all based on radiosonde data. Now, if you go ahead and constrain it using ground weather data, you get into these green curves here. So you've seen you've taken a huge range of possibilities and immediately, just with ground weather data, made a big difference. You can actually constrain it to probably, I guess, maybe plus or minus 10%, 1 sigma or something like that. Now, if you go ahead and add in your ability to use the measurement of the emission from the sky using the ground-based telescope, then you can narrow it down into this blue region. So now we're talking about something that's, say, plus or minus 8% or so, maybe even less than that. If you combine these two sources of data into your model with your neural net, you can constrain it down to here. And our projections are that we should be able to get it to plus or minus 0.2%. So in conclusion, we are building Mamba right now. We have parts sitting in the lab that are arriving. We're waiting for the mirrors. We had hoped that we'd have everything here and have it assembled and have it next to me on the stage, but that did not happen. That's the nature of building instruments. But we're getting close. The mirrors should be delivered tomorrow. So we intend to assemble it, and we will start our transmission testing in December. And we will actually have a full-up test with the Navy where they will confirm the accuracy of our system coming up next year. So some of the specifications are, we estimate the transmission should be measurable to 0.2%. The cloud cover, basically we'll be spitting out maps of where the clouds are. And this should be 14 or 16-bit data. The camera is 14 bits. We're going to stack the data, so we should be able to improve the dynamic range a little bit. We're hoping to produce water vapor as well. That is not the primary goal of the Navy's project, but I think we'd like to do that anyway. It is directly related to transmission. We'll have thermal infrared, and thus temperature maps of the sky. We plan on coupling this with a visible all-sky imager as well. And the image will come out at 1 to 50 hertz. And 640 by 480 is the full size of the camera. However, the projected size will be a circle onto the array, which will probably be about 420 pixels in diameter. And then there may be some additional parts of the array that we use to capture the missing part of the zenith cone, the obscured cone. And finally, we are going to try to make this into a commercial product, make it available in late 2016. So if any of you are interested in this, we'd be happy to talk to you. I guess the last thing I thought of just this morning was that this would be a great meteor camera. We should be able to see meteors day or night with it. I'm not going to say that this is an SSA camera. I really don't think we're going to see any satellites at GEO with this, but it's an interesting complement to a lot of SSA work. So with that, I'll take any questions.
time for a few questions.
I just want to update, the Rosicom on Tololo is in use every clear night. And if you go to the Cerro Tololo website, you can click on sky conditions and see what it's doing. And it's in use for the dark energy survey.
Oh,
and I would say, but all the telescopes on Tololo can access it. And what I would say, and I don't get a commission from you to sell it, but once you see one of these things in operation, you get addicted to it. And it's much more valuable than a seeing monitor in terms of seeing what the sky is like. So I'll give you my card because we'd be interested in getting one of your commercial ones.
Oh, thank you. Yes, we are in touch with the Rosicom team, by the way. So we're actually coordinating to some degree the building of the second generation of Rosicom.
You mentioned the central obscuration, but at least I don't recall you mentioning how low to the horizon it goes.
Yeah.
What's the constraint about how low it goes down towards the horizon?
Well, if I remember correctly, I think we're within 5 degrees of the horizon. But at the same time, you have to remember that it's an unusual telescope design. I don't know if I can bring it back here. Well, anyway, if you remember the picture of it, it's an unusual telescope design. And when you're down near the horizon, there aren't that many bundles of, I'll go back to the beginning. Yeah, as you get down to this area here, there aren't that many bundles that make it off the secondary and down through this very tiny hole in the primary. So it's not a magnifying telescope like a telescope is. Really, it's more like a lens or a camera. So your sensitivity drops right down there at the very edge. But the other thing we've noticed, and this always happens, is almost every site, there's going to be something in the way right at the horizon. So it's a fair question, though. We should test it. So we would like to go to Haleakala and test this, by the way.
Thank you.
I actually had a question. Have you considered using a three-dimensional numerical weather prediction model to give you your precipitable water? That way you don't have to worry about radiosondes that are spaced hundreds of kilometers apart.
It would be great to use that model. I assume that it is supplemented by satellite and radiosonde data, right?
Right, but it's fully gridded and fully three-dimensional every 10 kilometers or however high resolution you want to run the model.
We've not included that, but yes, I'd like to talk to you about that.
Okay, let's thank the speaker again. Our next presentation will be given by Danny Felton from Northrop Grumman Corporation, and he's going to talk to you about some of the atmospheric characteristics at Haleakala that we've been investigating to support LCRD.
Good morning. Let's see, I didn't get, there we go. So I'm going to talk a bit about not SSA, but about laser communications, and that's the work we've been doing for a number of years now. We're currently working for NASA. NASA, since it started launching satellites, has been communicating exclusively and very successfully via RF communications. But we think and hope that in the near future, in the next few years to decade or two, that free space optical communications are going to revolutionize the way NASA does communications with its satellites. And there are a lot of advantages to FSOC. You get a much higher data rate with the same swap. You can get many gigabits per second to even several tens of gigabits per second. The spectrum is not it's not regulated like the RF spectrum is, and the signals, the beams are so narrow. They're very they're not susceptible to interference and jamming and such as RF signals are. However, FSOC beams are much more susceptible to atmospheric conditions, primarily turbulence and clouds. So many clouds are just going to be basically a blockage to your signal. NASA in 2013 launched the LADI mission, and on that they had a lasercom terminal. And this small half-watt terminal demonstrated 622 megabits per second from lunar orbit down to Earth. And I think at one point they were able to download the entire day's mission data in 5 minutes via the laser versus their, a 24-hour download with their RF. And to build upon that, they are planning the laser communications relay demonstration here in 2 or 3 years. And that'll be a geosatellite with a ground station down to a ground station on Haleakala and another in Conus. And we are leading a campaign to measure and model the effects on the LCRD link. And so the success of any FSOC system is going to depend largely on how well we can mitigate atmospheric effects such as clouds and turbulence. So the objectives of our work are to quantify these effects, primarily clouds via remote sensing, geostationary satellites, atmospheric modeling, and I'll talk about all of these in more detail, and in situ data collection. And we want to develop a strategy to improve cloud detection on Haleakala, a very unique environment, and finally to develop operational concepts for mitigating FSOC link outages. And so we want to combine all of these, the in situ measurements with the remote sensing and the modeling to develop atmospheric mitigation strategies to improve FSOC performance. Like I mentioned, LCRD is going to have a ground station on Haleakala. It's a world-class location for a ground station. The summit is usually cloud-free, although you wouldn't know it from this week. It has a clean atmosphere and pretty good turbulence conditions. Clouds are usually held below the summit by the trade wind inversion, and I'll talk about that in a bit more detail. And so our goal is to detect and predict these, something happened in that last, so I think that's supposed to say, can the clouds be detected and predicted before they break the link? And these are a couple of pictures I actually took earlier in the summer at the summit, and you can see early in the day the clouds were below the summit, but then later the trade wind inversion on that day was right around the 9,500 feet or so, but the clouds were blown up and over the summit, and they evolve very rapidly, and a day like this would not be a good day for consistent laser comm. Before I go to the next slide, I want to make a slight diversion, and I'm going to show you a couple of my vacation pictures. My wife and I came a couple of days early, and we drove up to the summit on Tuesday, and I was excited. I was going to show her the domes up there and where we're going to put our instrumentation and all that. So we got up there and we went to the Park Service's summit parking lot, and we looked toward the domes, and that's what we saw. Okay, notice the timestamp on that, 9:45. Well, we turned around, started walking back to the car. I noticed the sky brightened 2 minutes later. So that's what you have to deal with if you're going to do successful laser comm. If this is your only site, you've got to do some kind of mitigation. You've got to switch to another site, something like that. But right now, we don't have the ability to detect and predict cloud outages on a second-by-second or minute-by-minute time scale. To get back to the trade wind inversion, so the trade winds are caused by the Hadley cell circulation. You get a persistent east or northeast wind here in the tropics, and where the cooler, drier air descends on top of that, you often get a temperature inversion where the temperature increases with height, such as we see in this cartoon here. And temperature generally decreases with height, but at this interface you get an increase with height and a drying of the atmosphere. And at that, here on Haleakala, where the mountain goes to about 10,000 feet, you get often the summit will stick out above the clouds, and that's what makes it a good site. Okay, I'm going to talk a bit about some of the tools and methods we use for site characterization and atmospheric modeling. For a number of years, since the mid and late 90s, we've been collecting GOES and other international satellite imagery. And we developed the cloud mask generator to use this multispectral data to create cloud masks, cloud-no cloud decisions at every grid point. And you can see here a loop of some of the satellite imagery over the Hawaiian region. You can see the long wave infrared In the upper left panel, the visible during the day, or what we call the fog product at night, that uses the long wave and short wave imagery. And you can see the cloud mask in the lower left developed from those different products. And then the cloud mask over Maui itself. And embedded in that is a whole sky imager image from the AMOS site up there. The benefits of the geostationary satellite remote sensed data is it's available globally about every 15 minutes. And it's available at 4 kilometers at night and 1 kilometer in the daytime. And this is very useful for getting long-term statistics basically anywhere in the tropics or mid-latitudes on Earth. But it does have limitations, specifically on a site like Haleakala, where the terrain changes so drastically over a short horizontal distance. So on a day where you have clouds that are legitimately just below the summit, that 4 kilometer or 1 kilometer grid point contains terrain that might vary from 10,000 feet down to 9,000 feet. And so part of the grid point is going to be legitimately cloudy, part's going to be clear. What decision do we make there? Well, there's probably no good answer based on the satellite data by itself, so it needs to be supplemented with something else. Let's see. Oh, shoot. All right, so another tool we use is numerical weather prediction, like Randy mentioned a few minutes ago. And specifically, we use the Weather Research and Forecasting, or WRF model. And we use this to forecast cloud outages. We also, several years ago, modified the standard version so that it computes optical turbulence. We compute the refractive index structure function and get the astronomical seeing parameters from that. We also use it to predict weather conditions like wind and precipitation. And some of the benefits of this are that it provides not just a characterization of what's happening now, but a forecast of hours and days in the future. It provides time-varying 3D output, so we can see the structure of the atmosphere, where clouds are occurring at multiple layers or something like that. We can get those soundings, those thermal soundings, so we can see where the temperature version is predicted to be a few hours from now. We run it currently over Hawaii at 1 kilometer horizontal resolution and about 50 to 100 meter resolution in the boundary layer. But some of the limitations of the NWP modeling is it uses relatively coarse input data, 25 to 50 kilometers from the National Weather Service. It's going to have trouble, again, seeing subgrid scale clouds. It's not going to forecast individual cloud elements or anything like that. And there are general uncertainties in NWP modeling. You can see on this day that it gets that typical cloud pattern around the summit very well. Two more instruments I'll discuss here that do not exist on Haleakala now, but we hope to, working with NASA, to get those put up there the next 6 months to a year. But you can see here the benefits of a whole sky imager and getting these small scale, dynamic, rapidly evolving clouds, something that you're just not going to see with the satellite imagery. And this is going to be very important in those second by second and minute by minute link decisions, handover decisions in an operational FSOC system. The whole sky camera that we plan to use is going to be infrared, so we're going to get day and night imagery. We also plan to put a ceilometer up there, which is a ground-based LiDAR, and it will tell us cloud heights, cloud thicknesses, and give us some estimate of a cloud fade or an optical depth of the cloud. And we hope to use these two instruments in concert to develop a cloud fade for the whole sky when we're using an operational system. With our CMG data, cloud mass generated data, we've developed long-term statistics, and I'm showing here the average mean or the mean cloud amount for the Haleakala region by month. Let me see if I can play that again. And you see here the cloud amount varies by month. It also varies by location. You can see, you know, the windward side of the Big Island there is cloudier, as you would expect. You can see the peaks of Mauna Loa and Mauna Kea, as well as Haleakala, are generally cloud-free. And this data has been validated in several field campaigns. And from this data, we determined that Haleakala is cloud-free about 70% of the time. With the WRF model, with our NWP modeling, I mentioned earlier that we model turbulence. We model the refractive index structure function, CN squared. And I ran about 2 years of simulations with WRF over Haleakala. And this shows you a diurnal cycle here in the lower left. We can see that the R naughts get smaller or more severe. The turbulence is more severe in the midday when the daytime heating is most intense, and it's more benign. They're larger at night. So WRF is able to produce the diurnal cycle. We also noticed that the R naughts tend to get worse under strong winds and worse when the wind is blowing from the east and northeast, when the trade winds are dominant. And this agrees with some other data that we've seen in the literature taken from the day-night seeing monitor that's been located on Haleakala in the past. And finally, the trade wind inversion. So, like I mentioned, the trade wind inversion typically caps the clouds to a particular altitude. And we looked at a couple of years of radiosonde data from Hilo, and you can see here that the median height of the trade wind inversion is between 7,000 and 8,000 feet, a couple of thousand feet below the summit of Haleakala, and that's what keeps the summit cloud-free most of the time. In fact, when the trade wind inversion is present, it's below the summit about 85% of the time. And we also see in the data, when we combine the CMG and the inversion data, that clouds are less likely to obscure the summit when trade winds are dominant, when they blow from the east or northeast. And you can see in this wind rose, these longer red bars indicate how often the wind blows from that direction. And the blue numbers, which you may or may not can read, indicate the cloud amount. And the cloud amount, or the cloud probability, is in the 20%, 25% range when the trade winds are dominant. But when the winds are blowing from the south or southwest, the cloud amount or probability of clouds is more like 35 to 45%. Okay, and two case studies here from this summer. One shows a strong trade wind inversion, and I don't know if you can see it, but here in the SKU-T diagram, there's a strong capping inversion about, I think, 7,800 feet on this day. And you can see here the summit is clear. The clouds are held to about 8,000 feet. And when we modeled this day with the WRF model at a 22-hour forecast, it produced that cloud pattern very well. Okay, so this is a day on which it would be easy to forecast good laser comm conditions. However, on a day that's been more typical of what we've seen this week here, the trade wind inversion was non-existent. There's no increase in temperature, no drying out of the atmosphere anywhere near the summit or below the summit. And indeed, we see on that day that clouds obscured the summit. And so we hope to be able to use this inversion data along with other data to predict when clouds are likely to obscure the summit. And finally, so the ultimate goal of this is to combine all the data, all the tools and products that I've discussed to produce a decision aid, something that will tell us what the current conditions are, what they're likely to be, in the near term, in a few seconds, a few minutes, a few hours, even out to a few days. And that data will come from different sources. It's likely to come from the whole sky imager and the remotely sensed GOES data on the minute time scale. out to a few minutes or an hour or two. Out at longer time scales, we're going to have to use NWP modeling, maybe cloud top heights to make estimates. And finally, and the goal of this is to trigger appropriate actions such as link handover, reduce data rate, or onboard storage to avoid those outages. Okay? And so I'll close with that, leave the conclusions up there if there are any questions.
Any questions? Yes, sir.
I was just curious, have you or anyone looked at how you deviate from these patterns in an anomalous set of conditions such as El Nino? What?
We have not looked specifically at Hawaii in terms of El Nino. It's going to be very site dependent, and this is a strong El Nino year, so it'll be interesting to see, compare this year back to 1993 or something to see if there were any clear patterns that were dominated by El Nino. Yeah.
Thank you.
So this morning I'm going to provide some background and frame the problem, and then Matt's going to come up and talk about methodology and results. So we're going to talk about computing PC and PC errors, some basics on atmospheric drag, the model that the JSPOC uses for the atmosphere and their solar storm model, determining conjunction event sensitivity to the atmospheric drag mismodeling, and then the tool, the space weather trade space tool that we built to examine that sensitivity and the results that we found from the tool. So, as most everyone already knows, probability of collision represents the probability that two satellites will come within a specified miss distance of each other, and generally it's calculated by the integral shown there, where R is miss distance, C is the combined covariance for the two objects, and A represents a combined size for the two objects. So the calculation includes the uncertainty in the state estimates as part of the covariance. So when you evaluate the PC for a particular close approach event, you have to know, is it realistic and is it complete? If it's realistic, then the errors are reflected accurately. And the JSPOC recently added some improved consider parameters to their methodology, and that's really improved covariance realism for them. But then, is it complete? And so you have to look at all these different error sources, and some of them are well known, like position estimates, but some are not so well known, like satellite sizes, and atmospheric drag is a really challenging one, not only to know what it's doing, but also especially to predict it out into the future. So the atmospheric drag is represented by this equation, where beta is the ballistic coefficient, a function of the area and the mass of the object. Rho is the atmospheric density, and V is essentially the satellite velocity with the effect of the atmospheric rotation relative to the satellite being acknowledged. But the beta and rho are not separable as part of this equation. So because of their coupling, changes in the atmospheric drag can be modeled by looking at changes in the ballistic coefficient. And so looking at space weather and how it affects the atmospheric drag and therefore conjunctions, we can take advantage of that, and we will later in the presentation, as you'll see. So for a close approach event, you have some set of observations of the two objects that are used to do your orbit determination solution, and then you have to predict out into the future to the time of the close approach event. And the JSPOC has two models for doing that. One is dynamic calibration of the atmosphere, which is used from the time of the last observation to now, because it uses calibration data from various satellites that they take measurements, and it provides a definitive estimate of the drag. And then from now to the time of the close approach event, they apply their HASDA model. And so then owner-operators are provided with a conjunction data message, which provides the satellite vector and covariance at the TCA, and also allows the operator to calculate the probability of collision. So over the course of an event between now and the time of closest approach, you receive maybe one of these a day or maybe several, depending on how often the data gets updated, and the owner-operator has to decide what mitigation action they're going to take, if any. So that decision becomes complicated if there's a coronal mass ejection or some other space weather that affects the positions of the objects. And so how is the operator to know whether the maneuver that they were planning to make was going to make the event safer or not safer? And so Matt's now going to come up and talk about how we address that problem.
Okay. So let's begin by talking a little about Yukiya Bowman HAZDM 2009. This is the atmospheric model that's presently in place at the JSPOC for about 2 years since it was fielded. It was produced by Air Force Space Command A9 and Space Environment Technologies. And really, it's a heritage model from Yukiya 70, but most of the internal empirical models have been updated. Some of the cases they've been reformulated, in other cases simply the coefficients have been changed. As Lori explained, this employs DCA for optimized performance during the fit span and up to the present time. So if you have a vector that's 3 days old and you want to do a 6-day propagation, the first 3 days are going to base the atmospheric findings on the definitive results of these 100 calibration satellites where the drag characteristics are very stable, so they can actually back out the real atmospheric densities and use that. And then from the current time through the future, the predictive portion of Yukiya Bowman HAZDM is used. It accepts a broader set of solar weather proxy industries. There are 11 EUV parameters, whereas Yukiya 70 just used the solar radio flux and its long-term average. It'll take 6-day predictions of those indices and therefore actually apply the model or explicitly for a 6-day period rather than only 3 days and then propagating the set value at 3 days forward. And the kind of the releasable description of the improvement is accuracy predictions at the 72-hour point have been improved by 20 to 45%. It also has this interesting feature that predicts and implements the prediction of the variation due to solar storms. As you know, the solar storm can be detected essentially limited only by the light speed from the sun to the Earth. So about 10 minutes after the event, you know it's happened, but it can take 50 hours for the ejecta actually to reach the Earth, and really you can get some sense of what the storm is doing. Right now, that's usually how we respond to it. Geomagnetic indices start to fluctuate when those ejecta arrive, and compensations can be made, but you've got to wait the full period of time for that to happen. What you want to do is predict the effects right after the detection without waiting for that. So as you're propagating into the future where the storm is supposed to happen, you've already considered those effects in your propagation. So the JBH09 model has an anomalous solar storm prediction model, which was developed by SET. And what it does is it looks at the X-ray magnitude of the flare and uses that as a proxy for the mass of the ejecta. This gives the size and the severity of the storm. And then the flare intensity is used as a proxy for acceleration. So the integral of that gives the velocity. If you know the velocity, now you know the time until the storm's arrival, so you can predict the time of arrival. And then the heliolocation of the storm helps you determine whether it's going to be terrestrially relevant. Is it going to hit the Earth? Is it going to be a grazing blow? Or is it going to miss? So these three data sources are taken together. They're used to actually, well, the statements here is a little abbreviated. They're used to predict the so-called disturbance storm time, which is kind of the equivalent of A sub P. It predicts that geomagnetic index value. That's used to produce a set of temperature coefficients that are then fed into the density model. So simply by observing the solar storm at the 10-minute point, you now have a set of predictions of what the solar storm is actually going to do to the atmospheric density. One of the disappointments of this model, though, is it doesn't come with an error statement. So you get the prediction, but you don't get any uncertainty values on the prediction, and that creates a problem for us. And in a way, we're kind of worse off than we were in the past, because with the Yukiya 70, we never tried to compensate for these storms. So we didn't know how much the density was going to change, but we knew the direction it was going to change in. It was only a one-sided uncertainty. The drag was going to increase, we didn't know how much. Now we're trying to compensate for the solar storm, and that's good, but we can either over or undercompensate, and since the model doesn't give us any uncertainty data, we don't know which it is. So now we have to deal with a two-sided uncertainty rather than a one-sided one. So we need to understand each conjunction's sensitivity to density mismodeling. And there's a really simple way you can get some insight into this by systematically varying the ballistic coefficient. Because if you'll recall, we've got the coupling here between between the atmospheric density and the ballistic coefficient. So the overall resultant acceleration is equally affected by a change in either of those items. So if we want to know what would happen if the density changed, we can force a change into the model by changing the ballistic coefficient. And if we do that systematically, we can get an entire trade space of the effects of density forecasting errors. So we constructed a tool, it's really pretty simple, that does just that. For a particular conjunction, it varies the drag coefficient for the primary and the secondary satellites, plus or minus a half of order of magnitude in each direction, about the nominal value. And then we calculate the probability of collision for each of those grid points. And that allows us to construct this trade space. And we'll look at some of these in just a minute, where the x-axis gives you the variation in the ballistic coefficient of the primary, the y-axis gives you that difference in the secondary, and then the out-of-page component, the color, gives the resultant P of C value. Now, what's important to remember when you're looking at these, the absolute value of the PC isn't that important. What's important is the grid pattern of the contours, because that's where the information actually lies. And there are two things you want to look for. Is the response contoured or is it flat? And is the nominal value at a ridge if it's contoured or off the ridge? So here's an example of one of them, and we'll go through this a little slowly to make sure we know how to read these. Down here's the x-axis. This is the variation in the primary drag coefficient, plus or minus half an order of magnitude. And this is the same for the secondary. The nominal value, and therefore the nominal probability of collision, is right in the center of this graph. And the color here gives you the probability of collision. This is red, P of C on log space of 0, really of 1, very dangerous. This is 1 e to the minus 10, something you're not concerned about. But again, you don't worry about the absolute values, you worry about the contour pattern. So here's an on-ridge situation in which the nominal value lies right on the ridge. So if the drag is mismodeled, the P of C is only going to decrease, because if you move in any direction, it either stays the same essentially as it is now, or it gets smaller. So you can use the information you have at hand to say, if I remediate the conjunction or take action based on my nominal value, I know I'm being conservative. If there's uncertainty, the uncertainty is only going to make the situation better rather than worse. Here's a different morphology you can be presented with. This is the flat situation, where the entire trade space varies less than an order of magnitude. And this conjunction is very insensitive to drag entirely. Well, how can a conjunction be insensitive to drag? Well, imagine a situation where you've got two satellites coming right at each other. And this is the in-track direction. The risk of this collision is not dependent on the in-track position at all. It's dependent on these two components. Changing the in-track situation will only change when the conjunction happens, but not whether it will happen. So this is one of the situations that will produce a chart of this type. If you see one of these, you know the situation is not sensitive to drag. So again, you don't need to worry about mismodeling in the solar storm condition. You can go ahead and base your remediation decision on that nominal value. If you get this situation, then what you're facing is much less sanguine. Here you've got the nominal value. Here you've got the peak. And of course, you don't know where you're going to be on this trade space. You don't have any insight into the errors of the model. So things could get better, but things could also get worse. So in this situation, which we've defined as you've got ridges, so there's more than an order of magnitude in dynamic range over the whole trade space, but the nominal PC is more than half an order of magnitude from the peak. Here, you can't really tell the owner-operator anything. You can say, yup, things could get worse. Things could also get better. So here, the space weather trade space doesn't help very much in a decision support framework. So it really comes down to how frequently we observe each of these different morphologies, and that's maybe where the interesting part of this paper is. How often do we get an on-peak or flat situation versus an off-ridge situation? So we wrote some software to mine the data that we had. We've produced about 16,000 space weather trade space plots since we implemented the function about a year and a half ago. We categorized the results by orbit regime, and let me say a little bit about these orbit regimes here. The LEO 2 and 3, this is where most of our protected assets are, so we're most interested in the performance here. LEO 1 is a very high drag area, so that's also of interest, but maybe more as a curiosity. We don't have very many assets that we support there. And then LEO 4 and HEO 1 are very lightly populated. So in the plots, when you see some outliers here, they are outliers, but they don't concern us that much because it's really a very small number of objects in play. We do need to talk about the max PC of 0 situation. This is a special case of the flat category, and it's an artifice of how we actually run the software. if the probability of collision for an event exceeds 1 e to the minus fifth, we start generating space weather trade space plots. But as that event develops, if the PC rolls off and goes to 0, we continue to generate them through the entire length of the event because we've already told owner-operators about the event. We want to follow it through all the way to the time of closest approach. So these are officially flat situations. The entire thing is one color, and it's all 0. So we're tabulating those separately in the statistics because it's a degenerate case and is treated as such operationally. OK, so here's one CDF plot. And this looks at the ratio of the max PC to the min PC over the trade space. And what this is really trying to show you is how often is it a ridged situation versus a flat situation. And what you see here is that 80% of the cases have a dynamic range between 4 and 7 orders of magnitude across the plot. So most cases are ridged. And way down here, only a very small percentage have a ratio smaller than 1 order of magnitude or half an order of magnitude. So there are very few flat response cases. Most of them are going to be ridged. And again, these are those outlier orbit regimes that have very few cases in them. Everything else has been sucked right into the same performance in a CDF sense. So very few flat response ones. So now what we want to know is how often are the ridge cases helpful to us, meaning we're on the peak, versus not helpful, meaning we're off the peak. So here are the responses for that. And again, kind of the main part of the distribution here, what we see is that we're looking at the ratio of the maximum probability of collision to the nominal. And we see that for a difference of half an order of magnitude, which was our definition of the ridged situation on the peak, 60% of the cases in LEO 2 and 3, which are the orbit regimes we really care about, show less than half an order of magnitude difference. That means they're either on the ridge or they're flat. And we saw in the previous graph that there are very few flat cases. So about 60% of the cases here are on ridge, which is excellent. So the majority of the time, the tool results are informative for us. The results are somewhat worse, interestingly enough, for LEO 1 in the higher drag situation. It presents different orbital geometries and dynamics. But again, we don't have that many protected assets there. So here's kind of a summary of all the results. We've done it as a bar graph now, where each of the orbit regimes is shown here. This blue is the max PC 0, so you can see what the relative contribution is. These very small, kind of aquish lines are the flat response. Then this light green here is the on-ridge situation, which is the one that's informative for us, and up here, yellow, off-ridge situation. So you see that we're in the majority of the time, we're in the green, and it's a super majority if you throw out these blue parts and don't consider that as part of the percentage calculation. So most of the time, certainly a majority of the time, usually a super majority of the time, we have an informal or informative result from this approach. So in conclusion, we still don't have actual errors for this solar storm prediction model, but we can identify situations where we can make remediation decisions that are going to be insulated from whatever errors they do present. And then the tool that we put together here shows those situations through the contour pattern. And the majority of the cases are such that we can actually tell the owner-operator something useful about the situation, or at least show them that acting on the data they have is a conservative interpretation. How would the situation get improved? Well, I guess by improving the actual solar storm prediction capability, perhaps through a physics-based model. But that's a problem for space physicists. And that is all of our prepared remarks. And I'm ready to take questions.
All right, so yesterday I think they gave out the award for the guy with the longest title. I think I'm in contention for the guy who has the most co-authors. So I haven't checked the stats yet. So this was a very large group project. So we had members of the team from Northrop Grumman. Kevin Scrow works at SMC. And then scroll through the list, you get down to Nelson Benito and Ron Keton and Michael Starks. They're from AFRL. All right, so ionospheric scintillation. And I think yesterday we had a lot of the optical astronomers out here. They're familiar with scintillation in an optical sense in the ionosphere. It's a similar situation. It's just for electromagnetic waves. It's caused by a rapidly varying refractive index that's due to turbulence. There's waves in the ionosphere and every once in a while, you'll get some turbulent features associated with those waves. When you propagate radio waves through that, it does strange things. The most apparent impact would be anything that transits the ionosphere, so ground to potentially GEO or GPS level orbits. You could lose lock, you could lose accuracy on your GPS, you could lose your phone, you could lose your radio signals for your car radio or your handheld communication devices. So that's why people care. Those types of events are measured. We have ground beacons, ground terminals that monitor beacons from geostationary satellites, and also GPS as they go over. Those observations are collected up, and then we try to characterize those structures and then put those into computer models and predict where those structures will go. And so that's the whole point. We have a new model nowadays that was developed by AFRL. I'll go into a little bit more detail about that model and its genesis. And then that model was handed over to us, and we implemented that. So we took it from a research lab into an operational center out at the organization formerly known as the Air Force Weather Agency. Now they're called the 557th Weather Wing. All right, so when you were in high school or perhaps as an undergraduate, you were taught about the different layers of the atmosphere. And those were generally based on the rate of change of temperature with height. So that's the colored layers there. So you can see that, wrong button already. There we go. This is the part of the atmosphere here that most people know about, and that's where all the weather occurs. That only goes up to about 10 kilometers. Ionospheric scintillation is much higher up in the atmosphere. And what they didn't tell you usually in your general meteorology courses is that there are other ways to characterize the atmosphere. And in particular, in the ionosphere is a layer of plasma. Some of the other speakers discussed that. That's where high energy photons from the sun hit the molecules and strip off the electrons. So it does interesting things when you do that. The ionosphere has been known about since Marconi. You can bounce radio waves off of it, or you can propagate radio waves through that, but there's some refraction associated with that, and all of that is frequency dependent. So mostly we're interested in the F layer, so anywhere from 300 to 400 kilometers. That changes throughout the daily variation as the Earth rotates around. It actually goes up at night and back down during the daytime. Okay, so ionospheric scintillation occurs at that ionospheric F region primarily. It only occurs at night, and it's in this particular model, it's only modeled in the equatorial regions. Vladimir talked about some disturbances in the mid-latitude. There are also disturbances in the polar region, but those are different drivers, and this model doesn't address those. So for impacts, mostly we're talking about transionospheric transmissions, VHF and UHF frequencies. So that does include the GPS frequencies up at 1.5 gigahertz. All right, so again, back to the how do we do this? So there are networks of ionospheric sensors around the world that measure the variations in signal amplitude and phase. From those measurements, we can characterize the disturbance, but it's only valid for that particular geometry. And there's only that one spot along this total integrated path between the two endpoints. There are not enough of these sensors around the world to measure everything accurately, but we do the best that we can with what we have. In the past, there were these sensors, many more than there are today, in fact, and they collected up all these stats and they made these maps of historical areas where scintillation would occur. And so that was the modeling for many, many years of just a climatological version of scintillation and where that could impact you, but we didn't know for sure. That advanced along to a product called the OPSEND, which would have been somewhere in the 1990s, I believe. So they actually started taking some of the observations, marrying that up with the climatological version of the model, and tried to predict the impacts in a little more logical sense with a data-driven type model, but it was still based on the historical values. So now we've progressed along a little bit further, where now we have taken some of these climatological models and some of the other models out of academia that try to characterize the scintillation, try to predict where it will go and decay, and we're still working on the development of the scintillation, but once we measure it, we know fairly well what will happen to it. So AFRL did a study of a lot of these models and picked best of breed for each of the component parts of the various models to put together the model that we were putting into operations at AFWA. They did a validation study on that model and found that it was about a 90% improvement over the previous methods, which makes this a fairly sophisticated model at this time. Okay, so that's called the Scintillation Nowcast and Forecast Technology Baseline was the model that was delivered. It is a data-driven equatorial scintillation model only. It does use observations from two different networks, one called the CINDA network, the acronym spelled out there. That's managed by the Air Force Research Lab through Boston College and scattered in the equatorial regions around the globe. And then the Air Force through SMC and a contractor runs the ISTO network, which are similar observations, but with a little bit more modern receivers. So these ground stations receive signals from geostationary comm satellite beacons and also GPS as they're over the station. And along that path, they find these scintillating structures and try to characterize where those are. It's a very small point in the sky, but this is a plasma in the presence of a magnetic field. And when that happens, the structures get elongated. I think Vladimir had some pictures of that. You'll see that in the output of this model as well. So we know the physics that describe that, so the model will stretch those out, and then it will try to move those along in time. So we do propagate those to future times. We can predict as much as 8 hours into the future. Typically, once we detect them, they decay out before the terminator arrives, and so it's usually less than 8 hours anyways. And as soon as the sun comes up, the structures just are reset, they say, when the ionosphere starts to build back up on the day side. The other little drawback, I suppose, about taking the observations is that we only do those at one frequency generally across the network, at least with the geostationary beacons, and then we use another frequency, of course, for the GPS. And so that kind of brackets the endpoints of the region that's susceptible to scintillation. But you communicate throughout that region. And so we have a frequency scaling algorithm. It's a series of power laws that will allow you to take measurements at one frequency and predict the impacts at others. And then the most important part of this is, you got the weather guys always build these weather models for weather people, but most people don't really understand or care about that. What they want to know is what's the impact. And so this model has a very interesting feature. Once you find the structures and predict where they will be and how long they will last, you can turn that into an operational problem where you focus on a comm satellite and a comm satellite footprint on the ground and determine the impacts on any of the signals within that footprint to communicate with that satellite. And I'll show you a picture, it might be more apparent when you see that. Here it is right here. Okay, so this is a notional product from the Air Force Weather Agency's production system. So you see the elongated structures along here. Keep in mind that the observations would be just a pencil point at some point along that arc, but the physics in the model and the way that we know the plasma behaves in the presence of the magnetic field gets stretched along the magnetic field lines, and that's what you see in each of these elongated structures. And as it gets stretched along, there are preferential ways for that to manifest itself, and so the intensity varies along that as well, and that's based on those historical studies that I talked about earlier that the earlier models were built upon. So this product is unique for that ComSat right there in the center. A little hard to see, but there's a satellite footprint on there as well. So the way you would interpret this is if you want to communicate with that satellite from anywhere in this satellite footprint, the places on the ground that are covered by colored bars would indicate that there is a probability of scintillation keeping you from doing what you want to do for that particular frequency. If you want to know about GPS, you would pull down this bar right there and select the 1.5 gigahertz, and then any frequency in between. All right, so that's a little bit about the model, and and how that works. There's a little bit more detail in the paper along with references if you're curious about each of the parts. Research to ops, that's a tough thing for science in general. The Office of the Federal Coordinator for Meteorology even called that out in the Space Weather Strategic Plan. There's a lot of barriers to that. A lot of those are self-induced. You know, when you put your heart and soul into a prototype model, you don't want anybody to change it or touch it or mess it up. It'll ruin your validation. So that's a barrier to progress to get for your model to see the light of day. And so there are a lot of things that have to go on. The model has to behave, it has to share resources with other models that are on systems, it has to be secure. And normally you don't think about those things as a scientist. So then the IT guys come in, computer programmers, and they want to change your stuff, and that always generates an interesting scenario. All right, so how did we do this? We're on a contract with SMC, and so now if there are any program managers out there, you will probably start to bristle at this point as well. You know, normally you lay out all the tasks, you got to do these things for this amount of money, and here's your schedule, and then you keep track of that waterfall chart. Agile doesn't work that way at all. But it does allow you some flexibility to attack unforeseen problems and manage the change that must occur, and manage the impact and minimize the impact of change on you being successful. So here are the 12 principles of Agile. It's widely used in the computer programming IT world. I'm not a fan of using it for science, but as the tech lead for this, I was told I had to, and so we did. And I learned more about it, and I found the power of using Agile as we went along. To me, the most important thing is right in the center. Whoa, did it again. The motivated individuals, that has to be everywhere. The program manager, the people on the project, the people receiving the final product. And I was very fortunate in this project that we did have that. So when you have all the motivated individuals using the 12 principles of Agile, you can do the change management. The way you do that is by valuing the individuals that are on the project and the interaction between them, and not just pure process and pure follow the tools and be a slave to the tools. Working software is very important. You want to deliver code that works, not big, massive volumes of documentation that no one ever reads. That stuff costs money, and very rarely do I see someone picking out manuals for these things and reading through them, even the program managers that paid for it. Customer collaboration is very, very important. If you're a program manager on the government side and you're working an Agile program, you will be very involved. Be prepared. Much more technically involved than you would normally be. That prevents a lot of contract negotiation up front, and if you do everything in the contract, that really limits the developer's hands on what they can do. And if something comes up that's not in the contract, you have to go back and renegotiate all that. With Agile, it's just do good things, do whatever the program manager says. That interaction will help guide the requirements and get you to success, and spend more money on the software and not the contracts office. And then respond to change. Don't just set the plan. Everyone knows no good plan survives first contact. Agile will get you around that. All right, so there are some framework and some tools that are involved. That ensures transparency. Transparency is key. Everyone must trust each other. They must know. The tools are online. The developers are constantly updating those, so there's no need for status meetings, update meetings. You skip all that. If you want to know, you go to this web page and everything's right there for the program manager. Our cycle was following this. The program manager comes in. Everyone puts in the computer all the tasks that must be done to get this project to success, and then the program manager decides which ones would be worked on in the next sprint. That's put into this cycle here. We usually did this in about every 3 weeks. This cycle lasts about 1 week. You put individual tasks, assign those to the workers, and off they go and they do work. They meet each day in a really quick meeting that is talk about what they did yesterday, what they're going to do, and any roadblocks. And those roadblocks are taken care of by a Scrum Master that goes out and figures out why people can't move forward. At the end of the 3 weeks, you come back out, you do a demo, show how the software works, make sure all the features were integrated. You talk about what went good, what went wrong, and then you start all over again, making sure that the program moves along and moves forward. Lessons learned, what we did learn here was the model came to us with the assumption that it was ready for operations. What we found was that it was not ready for operations. It had a lot of security flaws, had a lot of science flaws, and so initially we didn't have the original developers on contract. They were out of the picture, so we had to go back, get those guys on. Once we had them, then we could all work together to ensure any changes that we made would not impact the science and would still produce valid results. And in fact, in this case, produce better results because we improved some of the science algorithms. So we started thinking, how can you do this better? And so we came up with this rapid R2O concept where you include the IT guys up front with the scientists. And as you move along in the TRL, the science participation starts to decrease somewhat and the IT guys kind of take over. And what you end up with is a very robust, very secure, very technically correct, scientifically, product that works very well. All right, and that brings me to my summary and conclusions. Main thing to take away is there is a new capability out there at the 557th Weather Wing. If you want access to this model, just contact them and they'll make sure that you have access to that. And that's all I have for now. Thanks.
Any questions?
Yeah. The over-the-horizon radar community, of course, has done a lot of ionospheric modeling. So what would you say is the relationship between the scintillation model and the sort of total ionospheric models that they generate?
Well, I'm not 100% sure what you're asking me. Typically with over-the-horizon radar, HF radars, you're going to bounce or reflect or refract, whichever word you want to use, and it depends on the frequency you're using too. You're only really interacting with the bottom side of the ionosphere. So the scintillation is not really as big a deal, and it's going to be more in the, it could be, but it's,
F1, F2 is a pretty significant contributor to
right, again, frequency dependent, but, and then, the wavelengths of HF much longer typically than the scale lengths of scintillation. This is more of a VHF, UHF type phenomenon.
So it's a scaling phenomenon.
Yes, yeah.
Okay, and, all right, I think that answers my question.
Okay.
Thanks.
Jim, what's the computational resource to run this model?
Surprisingly small. We're running it on, initially on just a couple of blades in our development environment, but it's not a supercomputer type thing like a numerical weather prediction model. We just use one core and it runs in about 7 to 8 minutes, and that's global.
Can you use the microphone, sir?
I think he said, what is the time window for scintillation nowcasting?
Scintillation nowcasting.
So by the time you sense that and return the observations, approximately 10 to 15 minutes have expired, and then it takes, another 5 to 10 minutes or so to process everything globally. So, 20 minutes is probably, is kind of that age at that point for nowcasting, and then we can forecast out to about 8 hours in the future. Did I get it?